All right, so whenever you're ready, let me know what questions you'd like to go over and we'll go over that.
All right, so 9.2, page 294. I don't understand the EQs.
Okay.
Whatever those mean anyway.
So when you have equivalence,
Equivalence.
let's just see what's going on here. But then,
They gave us kind of a chart on page 291.
just give me 1 second. I'm having a technical issue. Which I'm hoping to address quickly. On double pencil charge. Okay. Okay. So, so with the idea of equivalence, essentially the charge of the ion gives the number of equivalents per mole. Because sometimes instead of counting particles by moles, sometimes for ions, we count things by equivalents. So essentially the charge indicates the number of equivalents that you have per mole of that particular ion. So for example, if you have something like calcium +2 ion, the fact that calcium has a +2 charge tells us that there are 2 equivalents of calcium +2 per 1 mole.
Okay.
So it's almost like an equality, so to speak. You know, even if you have something like a negative charge, like
Right.
a phosphate ion, you know, for a phosphate ion, you have 3 equivalents of PO4 -3 per mole, or would be equal to 1 mole. So essentially, the charge indicates the number of equivalents that you have per mole of that ion. Essentially, it's just another way of counting, in a sense. You know, sometimes we count by the mole, and you could count by the mole for ions, but sometimes you can count by equivalents. So if you had 1 mole of calcium ions, that would be the same as 2 equivalents of calcium ions. If you had 1 mole of phosphate ions, that would be the same as 3 equivalents of phosphate ions. So essentially what it is that it's just another way of counting.
Okay.
And then the bottom line is that in any solution, the charge of the positive ions is always balanced by the charge of the negative ions. So for example, if you had a solution where you had 25, and they use milliequivalents a lot instead of actual equivalents, per liter of sodium ions, and you had 4 milliequivalents per liter of potassium ions, you would have to have 29 equivalents milliequivalents per liter of something with a negative charge associated with it. Because at the end of the day, the sum of the charges, in a sense, has to it has to add up to zero.
Right.
So how many equivalents per liter of positive charge you have coming from whatever ion sources, for positive ions and for negative ions, the sum has to be the same, so that essentially the overall charge, in a sense, adds to zero. All right, so those are really the big ideas in terms of equivalence and such like that. So in terms of looking at questions, if you take a look at something like, let's say 9.16, where you want to know the number of equivalents in each of the following. And letter A, I'll skip letter A. If I go to letter B, would be 0.5 moles of H plus.
Mm-hmm.
Right? So if we look at H plus itself, what we find for an equality based on the charge of +1 is that there's one equivalent of H plus per mole. So essentially one equivalent of H plus would be equal to 1 mole. And that's sort of based on the charge of +1. So now we can use that as a conversion factor. So if we have 0.5 moles of H plus, and we multiply by one equivalent, for every mole, then we have 0.5 equivalents of H plus in this example. So I'll give you one more. If you look at letter D, they want to know the number of equivalents in 2 moles of Fe plus 3. So based on looking at Fe plus 3, what would be the corresponding equality relating equivalents per mole? Well, you would have here that 3 equivalents would be equal to 1 mole. Again, that's based on the charge of +3.
Mm-hmm.
So we start in this case with 2 moles of Fe plus 3. And we're going to multiply that here by 3 equivalents for every 1 mole. And the reason why we're doing this, even going back to the example above, is because when we set it up in this way, the number of moles cancel. So in this case, if you have 2 moles of iron plus 3, that would actually be the same as 6 equivalents.
Okay.
Correct. So essentially what it is that essentially it's just another way of counting.
Okay.
Instead of counting ions by the mole, one of the other ways you can count ions is by equivalence.
So like A, because there's 1 mole and a positive 1, so it will just be 1 equivalent, and then you solve for it.
Well, for A, it's magnesium plus 2.
Oh, I'm sorry. I looked at 9.15. Sorry.
Oh, okay, so yeah, so we can go to 9.15. So you're right. So the charge is +1.
Right.
So the equality would be 1 equivalent equal to 1 mole. Because they're giving you 1 mole, then the answer would be 1 equivalent.
Okay. But like B of 915, it's only 1 charge. But then when you do the equation, you'll have the 2 moles, just similar to this one, just changing the to OH.
Yep, because it's still a 1. It's sort of like still a 1-to-1 ratio.
Okay.
So the 2 moles in that case would be equal to 2 equivalents. So
Two
basically,
equivalents.
if the charge is +1 or -1, the number of moles and number of equivalents is the same. It's when the charge is not equal to +1 or -1 that the number of moles becomes different from the number of equivalents.
Yeah. Okay. So let's do 919 or 920,
Sure.
either one of those.
Yeah. So let's look at let's take a look at 920.
Yeah, because then I can do 919 by myself and see if I can
Yes, absolutely.
do it.
All right. So Ringer's solution contains the following concentrations, milliequivalents of liter of cations. So you've got sodium plus, which would be 147 milliequivalents per liter. You have calcium plus, which is 4 milliequivalents per liter. Then
Okay.
we have calcium 2 plus, which would be also 4 milliequivalents per liter. So the question is, if Cl is the only anion in the solution, what is the Cl minus concentration in milliequivalents per liter? Okay. So really what I think it just comes down to is that they give us essentially, we don't have to convert here between
Okay.
moles to equivalents, because in this question, they've really already done that for us.
Okay.
They're telling us, in this case, not equivalents, but in milliequivalents, how many of each of these ions that you have, which sort of contribute to the overall positive charge. So what I would do here basically is just add up those 3 numbers. And what that tells me is that the total positive charge would be 155 milliequivalents per liter.
Okay. So that's that milli equivalents is already have done the step that we worked on just before this.
Yeah, it would have been, if they would have given us each of these in terms of number of moles,
Okay.
essentially we would have had to take that, convert it to equivalents,
Okay.
then almost convert that to milliequivalents. But in this type of question and in this textbook, I don't think they're going to have you do all those steps
Okay.
in terms of this type of question. They could give you a question where you take one of these ions and they give you the number of moles and convert that to sort of either a milliequivalent or a milliequivalent per liter if they tell you how many liters of solution that you have. But I don't think they would do that for all 3 of these ions,
Okay.
this type of question. So that essentially means for the chlorine, the total negative charge should be 155 milliequivalents per liter. And since chlorine is the only, or the chloride is the only anion that's present, then that really has to be the concentration of the Cl minus.
And they could have picked any chemical or ion, right?
Yeah, I could have been,
Okay.
especially for the fact that they're not having an involved calculation here. They could have said it's sulfate or bromide or oxide or phosphate. They've already done the work of converting the moles to equivalents. So really, it's in a sense, in this case, it just should be about adding it up.
And they were all positive charges. And so then they gave us a negative charge. And that's what we're looking for. Is that
Well,
negative
yeah, and they
charge.
tell us that the chloride is the only negative ion,
Negative charge.
only anion present. So that has
Okay.
to account for all the negative charge.
Okay.
So it would have to account for 155 milliequivalents per liter.
Okay. And then 1 equivalent equals 1,000 milliequivalents.
Yes. So yeah. So 1 equivalent, absolutely, based on the prefix of milli, would be 1,000 milliequivalents.
Okay.
That's correct. Yes.
All right, my next question is 9.3.
Okay.
I'm not quite sure if I understand how to find out if it's saturated or unsaturated.
Okay.
Like
So,
if they give me,
go ahead.
like 923, they give me, I add this to the solution and it didn't change the size,
Okay.
okay, I get that. But when I had to do the math in 9.25,
Okay. Okay.
I couldn't
Yep,
quite get there.
no problem. So let's take a look at it. So let's take a look. I'll do 926. So we're leaving 920. Okay. So for 926, letter A, okay, they want to know the following solutions would be saturated or unsaturated at 50 degrees. So for letter A, they have adding 25 grams of KCl to 50 grams of H2O. And the
We're
temperature,
supposed to use that chart.
yes.
Okay.
Yes. Because what that chart tells us is that and the temperature is important, because solubility is affected by temperature. What that chart tells us is that at 50 degrees Celsius, you can dissolve 43 grams of KCl will dissolve in 100 grams of water. So essentially, if you have 100 grams of water at 50 degrees Celsius, any amount up to and including exactly 43 grams of potassium chloride will dissolve in water. But once you go above 43, so I'm talking like 43.01, 43.02, that 0.01, 0.02 and anything excess will not dissolve in the water, because that 43 is exactly when the solution becomes saturated. You have the maximum amount of solute that can dissolve in that specific amount of solvent. Now, the trick to this question is the fact that they don't give us 100 grams of water, they give us only 50 grams of water. So there's a couple ways to approach it. What I would do is I would use the facts that 43 grams of KCl will dissolve in 100 grams of H2O at 50 degrees. But if I have only 50 grams of water, which is half the amount of 100, then only 26 grams of KCl will dissolve. If you have half the amount of water, half the amount, not 26, sorry, 26.5. 26 and a half. Half the amount of so only half the amount of the potassium chloride will dissolve. So
do we go 43 divided by 2?
yes,
Taking half of it?
yeah, because if you have
Okay.
half the amount of water, then only half the amount of solute can dissolve.
I have 21.5.
Yeah, it's because my math is pretty bad without the calculator.
Okay.
Oh, you're right. Thank you. Yeah, that would have come out to 40s. Yeah, that would come out to the higher 40s, above 45. So yeah, so only
Okay.
21 and a half, correct. Thank you. So that means only 21 and a half grams will dissolve. So if you add 25 grams
To the
that means-
21.
Yep, only 21 and a half of that will dissolve. And therefore, not all of it is going to be dissolved. So anything above 21 and a half is just going to sink to the bottom. And essentially that means,
Okay, so then we subtract those two.
right. And if you want to know exactly how much is not going to be dissolved, Then
Okay.
you would do the 25 minus 21.5. And this one I'm gonna get right. I believe it's 3.5 grams. Will not dissolve.
Okay.
So that 3.5 grams will basically just sink to the bottom.
So OS will dissolve. 3.5 will not dissolve. Okay.
Yep.
Can we do another one of that one?
Sure.
Either B or C?
Yeah. Let's just go to B. All right, so for B, we have adding 150 grams of sodium nitrite or nitrate, sorry, NaNO3, to 75 grams of H2O. All right. So again, we go back to the sort of reference table that they gave us. And what we find is that at 50 degrees Celsius, for sodium nitrate, 110 grams of NaNO3 will dissolve in 100 grams of H2O. So again, what I would do is I would manipulate this to figure out, okay, at 75 grams, how many grams of sodium nitrate are going to dissolve? Now, the math here is a little bit more complicated, not much, but what I would do essentially is I would just sort of set up a proportion that if you have 110 grams of NaNO3 that can dissolve in 100 grams of water, you know, how many grams of NaNO3 will dissolve in 75 grams of water. So we would cross multiply and divide. So 75 times 110 divided by 100. So that gives me 82 82.5 grams of the sodium nitrite. Okay, so it's only that amount that's going to be able to dissolve in 75 grams of water. So if we're adding 150 grams,
grams.
yep. So if we're adding 150 grams, only 82.5 will dissolve. And therefore, once again, we're dealing with a solution that is saturated. And in fact, in this case, if we do the 150 minus 82.5, 67.5 grams do not dissolve.
Okay. Seven. Okay, so what if the temperature changes, like in 9.27 or 9.25, 28?
Sure. So let's go to 9.28. So a solution containing 80 grams of sodium nitrate and 75 grams of water at 50 degrees Celsius is cooled to 20 degrees Celsius. All right. So we've got 80 grams of NaNO3 in 75 grams of H2O at 50 degrees. And it's cooled to 20 degrees Celsius.
That means it's going to slow down dissolving.
So first thing I would say is at 50 degrees, let's figure out if the solution is saturated or unsaturated. That's
Okay.
that's what I would probably do first. So we saw in the previous example that at 50 degrees Celsius, you can have 110 grams of NaNO3 can dissolve in 100 grams of water. And we did the work to show that 82.5 grams of NaNO3 will dissolve in 75 grams of water at this temperature. So what does that mean? It means that at 50 degrees Celsius in this example, we have an unsaturated solution. So in other words, if you look at it, you wouldn't see any solid. You basically would see all liquid. So now what happens? So now we cool the solution to 20 degrees Celsius. And if we go back to the reference table, we find that 88 grams
Oh,
of NaNO3 will dissolve in 100 grams of water at this temperature. So now we want to do sort of like what we did before. You know, if you have 88 grams of the NaNO3 that can dissolve in 100 grams of water, well, then how many grams of NaNO3 can dissolve in 75 grams of water at this temperature?
okay.
So we'll again plug that into the calculator. So 88 times 75 divided by 100. So at this temperature, only 66 grams of sodium nitrate will dissolve in 75 grams of water. So letter A, how many grams of sodium nitrate remain in solution? Well,
20.
there was 80 grams, but since we cooled it, only 66 of those 80 are able to stay in solution. And that leads us to letter B. How many grams crystallize out upon cooling? Well, if we started with 80 and 66 are going to remain in solution, well, then that tells us that 14 grams crystallize out. Because if you were to watch this as you were cooling, all of a sudden you would see solid form inside the liquid. That now is because the solubility of the sodium nitrate in water at the lower temperature has decreased, like most solubility of solids do at cooler temperatures. The solubility tends to decrease. So that's exactly what you find in C. So those would be the two answers for A and for B.
Okay. Okay, so 933
Okay,
A, I didn't get the right answer that's in the back of the book,
okay,
but I got B and C right. So that's when I'm like, okay, what did I do wrong?
okay, not a problem. And I'm going to show you the difference because it's a subtle difference. So let's look at
Okay.
934 and let's start with B, which is a similar question.
Similar. Okay.
So B says 2.0 grams of KOH and 20 grams of H2O. What makes this different from the 34 for A and C is that in B, they actually don't specifically tell us the total number of grams of solution based on the wording. Because
Okay.
if you look at A, and I'll just put A down for 34, they tell you 75 grams of NaOH in 325 grams
Instead of and. Oh my gosh.
of NaOH solution. So the difference here is that in A, the 325 grams is the total mass of the solution.
Okay.
But for B, the total mass of the solution has to be found by adding them both together. So the total mass
Oh,
of the,
okay.
so the total mass of the solution in B is 22.0 grams. Because in B, you're taking potassium hydroxide, 2 grams of it, and you're taking 20 grams of water and you're adding them together. But
Okay.
for A, the components, whatever they are, have already been added
In there.
together.
Okay.
That wording, and it does catch students by surprise, that wording is the key difference. So for B, then to find the mass by mass percent, you would take 2.0 grams over 22.0 grams and multiply that by 100%. So I believe that comes out to 2 divided by 22, about 9.09%.
Okay.
Where the common mistake students would make with this one is they would put 10% because they would do 2 divided by 20. It's
Right.
not, it's just based on the wording. It's, 2 divided by 22. So that was good because this was one I was definitely going to talk about.
Yeah. Okay. Um, so 9.48. Oh no, it's over here. Okay, 9.49. Okay, I think it's 9.49.
Okay.
Again, I got A and B, but then when I get to C,
So 9.49C.
Yeah.
Let's look at, I guess, let's look at 9.50 C.
Okay.
So we have, for each of the following solutions, calculate the milliliters, so ml, of 2.50 molar potassium sulfate solution to obtain 1.20 moles of K2SO4. Okay. So remember, molarity is equal to moles per liter. So if we want to solve for the number of liters, the number of liters would be equal to the moles over the molarity. That's one way of doing it. The other thing is you could also use molarity as a conversion factor. Because if you have 2.50 molar, you could write that as 2.50 moles
Mhm.
being equal to 1 liter. So if I choose to do it that way, I have 1.20 moles of K2SO4. And then
Okay.
using the conversion factor for the molarity, I would do 1 liter over 2.50 moles. Because now when I do that, the moles cancel, so I have to divide the two numbers. So if I do 1.2 divided by 2.5, I get 0.48 liters. And then they want the answer there in milliliters.
Milliliters.
So we would multiply that by 1,000 milliliters over 1 liter. And that brings me to 480 milliliters. So I think if you apply that to 49C, you should come up with the right answer.
Okay, I think that's all my questions.
Okay, great. All right. So then I'm just probably going to do just some other examples of some things come across. But those are some good ones. Those were definitely some good ones. All right, so let's I'll do some more calculation.
There we go. Okay. Yeah, I figured out what I did wrong in that one.
Okay, good.
I did 0.5, not 0.05.
Okay. Okay. So if that's the only thing, then you've got the right technique, which is great.
Yeah.
Okay.
Okay.
Awesome. All right. So let's just run. I'm going to run through some other calculation ones. So 36 bottle of champagne is 11% volume by volume alcohol.
What page are we on?
Oh, I'm sorry, 305, 9.36. So 11% volume by volume alcohol. If there are 750 milliliters of
Okay.
champagne in the bottle, what is the volume in milliliters of the alcohol? All right. So I think sometimes some of the tricks to these questions is figuring out which is the solute and which is the solvent. So essentially, when they say a bottle of champagne is 11% volume by volume of alcohol, then to me, the alcohol is the solute and the champagne is the solvent. You know, because there's other additives to the champagne besides just the alcohol itself. So that's one of the challenges with some of these questions, is identifying solute and solvent. The other thing here is sort of work with the 11%. What you really want to do is you want to convert that 11% from a percentage into a decimal. Because remember, for all these different types of solution calculations, except for molarity, you sort of multiply by 100%. So what I would do is I would take the 11% and convert it to 0.11. So basically, the 0.11 should be equal to the volume of the alcohol over the volume of the champagne. And that would bring me to 0.11 is equal to, let's say, X over 750 milliliters. You can leave it in milliliters. You don't have to change it to anything else. So 750 times 0.11, that essentially would mean that the amount of alcohol would be 82.5 milliliters. Okay. So that's one example of that type of question. In terms of 40, mass by volume percent, pretty straightforward. Number of grams divided by the volume, whether it's in essentially milliliters or liters. Usually I think it's in grams per milliliter for the most part for that type. When you do mass by mass, it's over, it's grams over grams. Volume by volume is milliliters over milliliters. The mass by volume is interesting because you have two different units that essentially, quote unquote, don't cancel. But for mass volume percent, we divide the numbers anyway. So just keep that in mind, that if you just divide the numbers essentially to get that right. What else? Let's see, 42. Calculate the grams or milliliters of solute need to prepare the following. 150 grams of a 40%. All right, so let's look at one from 42. So 9.42. Let's take a look. So we've done mass by mass. We did a little bit volume by volume. Let's do B. So let's do 450 milliliters of a 2% mass by volume KOH solution. All right. And basically they want to know here, we'd want to know the number of grams of solute. Okay. So again, the first thing I would do is I would take the 2% and let's divide that by 100 to convert it to a decimal. So that would be 0.02. So the 0.02 would be equal to the number of grams of solute over the milliliters of solution, which in this case leads us to 0.02 is equal to X over 450 milliliters. And in fact, if you wanted to leave out the unit, I would probably be okay with that in this case, because we're dealing with a mass by volume, where again, the units don't exactly match up. But if you take 450 and multiply it by 0.02, you get exactly, and we can put 9.0 grams of solute, right? So for mass by volume, one of the things don't panic with is about the units. Grams and milliliters usually don't cancel, but that's just the way sort of the concentration is expressed. And you can really do the mathematics in a sense as if the units were going to cancel with each other. Okay, let's do an example of, let's go to 44. And let's do 44A. So here they want to know the number of grams of 2.0% mass by mass NaCl solution that contains 7.50 grams of NaCl. Okay, so remember, first thing we'd want to do again is take the 2%, and let's convert that into a decimal form by dividing by 100, so 0.02. So that 0.02 is going to be equal to the number of grams of the solute over the number of grams of solution. Now, in this case, they give us the number of grams of NaCl. And if you have an NaCl solution, the sodium chloride is going to be the solute. So we have 7.50 grams of the solute. And what we're looking to find here is the number of grams of solution. You know, they want the number of grams of a 2% mass by mass sodium chloride solution that contains 7.5 grams of NaCl. So in this case, we're going to take the 7.5, we're actually going to divide it by 0.02. And therefore, X comes out to be 375.0 grams. So if you took 7.50 grams of sodium chloride and you had it in a sodium chloride solution that was 375 grams, and again, notice I use the word in, the mass by mass percent would be 2%. All right. Let's take a look at 46C, because there's a couple things with this one that we should talk about. And here in 46C, they want to know the molarity of a solution where you have 30 grams of sodium hydroxide in 350 milliliters of a sodium hydroxide solution. Now, a couple things. First off, don't forget molarity is equal to moles per liter. And if you think about that with the information you're given, technically right now you have neither one. Because we don't have moles, we have grams. We don't have liters, we have milliliters. And in fact, do we have to adjust both? Yes, we have to adjust both. So for sodium, again, so how do we go from grams? Let's do the grams of sodium hydroxide first. You know, how do we go from grams to moles? Well, as we learned, the way we convert between grams and moles is that we have to use the molar mass. Again, whenever you convert between grams and moles, you have to use the molar mass of that substance. So if we use the periodic table, sodium 22.99 grams, oxygen 16.00 grams, hydrogen 1.01 grams. If we add that all up, 22.99 plus 16 plus 1.01 gives us 40.0 grams, which would be equal to 1 mole. So we take the 30 grams of sodium hydroxide, and we're going to multiply it by 1 mole over 40.0 grams. And that gives us 0.75 moles of the NaOH. Grams cancel out. And that gives us, and I'm pretty confident, but always double check. Yep, 0.75 moles of NaOH. Now, for the 350 milliliters of solution, I need to multiply that by 1 liter over 1,000 milliliters. Because in order to use molarity, the volume has got to be in liters. So that gives me 0.35 liters. So now I can figure out the molarity. I take the 0.75 moles over 0.35 liters. 0.75 divided by 0.35. And that gives me essentially a 2.14 moles per liter solution, which is the same as 2.14 molar. Right? So one thing I always like to point out with molarity, and a lot of times, you're given, or not a lot of times, but sometimes you're given the volume in milliliters. In order to calculate the molarity correctly, you have to be able to convert that into liters. And then sometimes you're not given the number of moles. Sometimes you are given the molar mass of the solution. So I just wanted to take a few minutes to go over that. All right. Let's jump to something like 9.10. And this is on page 293. So here you have, write a balanced equation for the dissociation of each of the following strong electrolytes. In water. So one of the things to remember, in a sense, is the difference between strong electrolytes and weak electrolytes in terms of their dissociation. What do we talk about when we talk about this idea of dissociation? Dissociation is the separation into ions. Because in order for you to be able to conduct electricity, in order for a solution to be able to conduct electricity, you have to have ions present in solution. The more ions that you have, the more electricity you're going to be able to conduct. Strong electrolytes dissociate completely in solution. And that's why in solution, they exist only as ions. When you take a look at an equation for their dissociation, you only see a single arrow pointing towards the right, which is what you see in most chemical equations. Now, just to mention, when you talk about weak electrolytes, they dissociate only partially in solution. So in equations, how do we indicate that? We indicate that with a double arrow. And sort of the way I like to consider a double arrow is a two-way street. You've got the cars going in both directions. In terms of a chemical equation, that means that not only are reactants converted into products, but products are converted back into reactants as well. Now here, we're considering only strong electrolytes. So basically, if you look at the different examples, all we really want to do is figure out what ions they're going to produce, but then also it has to be balanced. The equation has to be balanced. Now, when you think about lithium bromide, it's pretty straightforward, because if you take lithium bromide and put it into solution, if you put it into water, and remember, water above the arrow indicates that it's a solvent, you get Li plus and Br minus. And essentially, the equation is balanced, not only in the number of atoms, but in charge as well. There's no overall charge on the reactant side. There's no overall charge on the product side, because the +1 and -1 adds up to 0. But then when you get to C, in something like copper 2 chloride, we know that chloride is always going to be -1. And based on the chemical formula here, we can figure out that copper is +2. However, right now, this equation is not balanced. And one way you could very quickly see that is that you have 2 chlorine atoms on one side, on the reactant side, and you only have 1 chlorine on it. Yes, it's an ion, but you only have 1 chlorine on the product side. So in front of the Cl minus, we have to put a 2. And if you look, that also helps with the charge issue, because prior to putting the 2 there, the charges weren't balanced. Now, again, you have a compound where the overall charge is 0, and therefore the overall charge of the ions has to add up to 0 as well. And when you have +2 and 2 -1s, +2 and then -2 adds up to 0. Okay. So I did want to just take a look at a couple of those, just to indicate a little bit about reactions and stuff like that. Okay. One of the other things that you come across in this chapter is using the solubility rules. Okay. Now, I will tell you that you don't have to memorize the solubility rules. If there's a question or two on solubility rules, I will reproduce, in a sense, the chart that's there. I think that's a lot to memorize. You have enough to memorize, and I don't think memorizing the solubility rules is that really important. You usually get it in a tabular form. But the question is, you should be able to, or need to be able to, use the solubility rules. The chart they give you in the textbook essentially talks about things that are going to be soluble in water. So basically, when your positive ion is lithium, sodium, potassium, rubidium, cesium, or ammonium. When your anion is nitrate, acetate, which is the C2H3O2 minus, then you get to chlorine, bromine, and iodine. And essentially, all of those salts are going to be soluble in water, unless the cation, the positive ion, is silver +1, lead +2, or Hg2 +2, which I think they call mercury 1, but those are not soluble. Those are insoluble in water. And then for sulfate, they are all going to be soluble in water except for barium, lead +2, calcium, strontium, or mercury, Hg2 +2. That's really where the tricks are, because the chart really talks to things that are soluble, but those are the exceptions. And those are the ones that you have to watch out for. And then basically, ionic compounds that don't contain at least one of these ions in the chart are usually insoluble. Okay. So let's just take a look at 932. And here's the compounds. We've got AgCl, we've got Ki, we've got Na2S, we've got Ag2O, and we've got CaSO4. Okay. So let me just fix the Ag2. Ag2, O. All right. So again, let's go to the solubility rules. So the first one is silver chloride. So, you want to look up the information that either speaks to silver or speaks to chlorine. And basically, I would use the idea that assuming that it's soluble, in a sense, and let's see if it truly is or not. Because again, the chart to me really speaks to things that are soluble. So when I look at the chart, I find chloride, Cl minus. And that tells me that all chlorides are soluble except when combined with silver plus 1. And silver plus 1 is the ion that you would have in silver chloride. And therefore, even though most things with chloride are soluble, this compound in water, and this really speaks to solubility in water, this compound is going to be essentially insoluble in water. The interesting thing about ionic compounds and solubility in water is that no ionic compounds are really truly insoluble in water. There's always at least a small amount that dissolves, but sometimes it's so small that we essentially consider to be insoluble. So we just go by what the rules say, in a sense. Potassium iodide. So in this case, when I look at the chart, I see potassium, so that's going to lead to soluble. And I also see iodine in that chart. So yeah, I mean, both of those ions usually lead to something that is soluble. So potassium iodide should definitely be soluble. Sodium sulfide. So I see sodium as one of the positive ions. I don't see anything about sulfide. So that would lead me to the belief, based on the chart, that sodium sulfide would be soluble in water. Silver 1 oxide here. Now here, I have the silver with chlorine, bromine, and iodine with the exceptions. But in essence, I don't really have anything else about silver, and I don't have anything about oxides. So since neither one of these ions are really talked about in the chart, I would suspect this compound to be insoluble in water. Especially also dealing with the fact that, when silver's with the halogens, where most halogen compounds are soluble in water, and when you have it with silver, it becomes insoluble, then it should be really no surprise, in a sense, that silver 1 oxide should be insoluble in water as well, based on the solubility rules of the chart. And then the last one, calcium sulfate. So again, I don't see anything specifically about calcium, but I see sulfate. So most sulfates are soluble, except when combined with barium, lead +2, and calcium is the next one. So calcium sulfate insoluble in water, because it's one of those exceptions where most sulfates are going to be soluble in water. If you pair calcium up with sulfate, it's going to be insoluble in water. Okay? So again, don't expect you to memorize the solubility rules, but have to be able to use them. And I think that's about it for our discussion of solutions and such. Any other questions?
No, that's great. Thank you.
You're welcome. Stay well. Hope to see you next week.
Thanks.
You're welcome. Bye-bye.